Okay, hello everyone. Today is very glad to invite Satoshi Nawata from Fudan University to give us talk about the 3D correspondence. And here you are.
Okay, thank you very much for invitation. And I'd like to thank the people at Yale Center for invitation. Especially, I'd like to thank the this year. So my first PhD student was accepted to Yale Center, who is now organizer of this seminar. I really appreciate the consideration. Actually, Yao Center was his the dream position at that time, and then he's now at the dream place. So I hope he's going to, the organizer will work hard at the Yao Center. Anyway, so today, I would like to give some brief introduction to 3D correspondence. Last like 5 or 6 years ago, I don't remember, but I've been working on 3D correspondence. So I just give you some rough, like a broad review on the 3D correspondence. And then the first half of the talk will be very, very basic to the expert if you already knew the story. So maybe it's going to be boring, but I think it's better to introduce the basic one too. And later I will talk about the so-called the Z-hat invariance or quantum modularity and so on, which is nowadays hot topic, mainly the program read by the Sergei Gukov, Pavel Putrov, many others. But anyway, so that's the later part of the story, and then the talk is supposed to be 1.5 hours. But if you have questions, please feel free to ask. Okay, let's move on. The first of all, so let's recall the brain setup of the 3D setup. So you can see my writing, right? So the space-time is this space. So R times C2 times cotangent bond of 3 manifold. And 3 usually we consider the cross 3 manifold M3. And then so this is the 11-dimensional space-time. And then we wrap the we put the N and phi branes on the R cross CQ and times M3, so 3 manifold. So essentially, here's a schematic diagram. So that the total space of Calabi 3 for the cotangent 3 manifold, and you just wrap the M5 brane on this 3 manifold. And if you want to create a knot, you just put the so-called co-normal bundle along the knot K inside M3. So this is also Lagrangian submanifold inside a T star M3. So if you put place the M5 brane in the Lagrangian submanifold inside a Calabi 3 for it just preserves the half supersymmetry. And then we just look at the theory living on this 3-dimensional space, R cross CQ. And then if you look at this one, so you just you can have the full supersymmetry, which is indeed 3D n equal 2 theory living on this space. And then this Q is omega background parameter. And then on the other hand, here we just perform, I will introduce later, so we perform topological twist, so that here we have some so-called topological quantum field living in here, M3. And then it's depending on body of Q, so we're supposed to have here in the complex Chern-Simons theory. So since this is living on, and then this 3-dimensional n equal 2 theory is actually labeled by M3. Or if you include a knot K, so it's labeled by M3 and K. So that's and then in particular, in some special nice setting, it has a Lagrangian description. But most of the generic 3 manifold, it doesn't admit the Lagrange description. That's the case. And the later talk, mostly we focus on n is equal to 2, is U2 or SU2 case in this talk. But higher rank case also can be discussed, but there's some open problem in higher rank too. So SU2 case is well understood, but higher rank case is not so much studied so much. And in particular, so when Q, so Q and T is called omega background parameter. So for when T equal to Q case, where Q is C star variable, so the theory living on M3 is indeed so-called complex Chern-Simons theory, where the usual K is the integer, but here you have analytic continuation. And A is the complex Faraday gauge connection, and I will introduce later. And when generic T is not equal to Q, one can put this, one can preserve supersymmetry by putting this system into the cipher manifold M3. So in this setup is considered Agnagi-Shakirov, which is co-refined Chern-Simons. And so in general, so in general T, so the theory living of this space does not admit Lagrangian description like this way. But here there's a way to how to say compute a partition function. Any question on this slide?
Yeah, Satoshi, I have one maybe simple question.
Yes.
So here the Q, the definition of Q's involve K minus S, but in the action you have 2 copies. So
yes.
Is there for example, some conjugate of Q also involves?
Good question. So here, so you have, this is the holomorphic part, and this is anti-holomorphic part. If you look at this, if you replace this this system, so this is half. It's called half index or arc or just a cigar or but if you replace this space by S3, the S3, then northern hemisphere corresponds to holomorphic part, and southern hemisphere corresponds to anti-holomorphic part. So usually this S3 partition function admit the holomorphic factorization, holomorphic part, anti-holomorphic part. So therefore, if you replace this space by S3 or squash S3, one can see both sides. But if you consider this system, generically you can just see the holomorphic part.
Okay, I see. Thanks.
And then 3D, I didn't mention that the 3D correspondence is a duality between this 3D equals 2 space and the complex Chern-Simons theory.
Hi, I have a basic question.
Yes.
So for the gauge group of the complex Chern-Simons theory, is that determined by the big N? So
yes. So in this case, G, L, and C.
Okay, G, L, and C.
Yeah.
So
yes.
Thanks.
So here I mostly assume the G, L, and C or S, L, and C. And if you put the some whatever orient for it can be any generalization. But yeah, I'm not going to consider. And I think not so much study in D&E type. And also, so this is a big subject. I forgot to mention that I didn't cite all the people's paper. But I mean, I think some of the audience already made a lot of contribution. If you think the reference is missing, just tell me. I don't cite everything, so so just, I mean, if I miss some citation, I'm very sorry. Let me move on. Okay, so many of you know this theory living on the M5 range for the 62,0 theory, whose the symmetry is the SO6 Euclidean or Lorentzian SO1,5 symmetry times this SP2 R symmetry. R symmetry is SP2. I mean, the algebra is isomorphic to SO5, SO5, and if you put the theory on the R cross CQ times M3, then SO6 is decomposed to SO3 here times SO3 here. In fact, this is the holonomy is trivial, so but anyways. And then also we can decompose SO5 symmetry into the two pieces, SO3 times SO2, and then one can perform the so one can perform essentially this is the cotangent bundle. I mean the SO3 is the action of the cotangent fiber of T star M3. So you can just perform a topological twist on here. And what's left is the SO2 R symmetry, which becomes R symmetry of 3n equal to 2. And then the theory living on M3 becomes topological. And in particular, after topological twist, this SO5 acts on this 5 scalar inside in the 62,0 theory. But once you put the theory on the this space, the theory decomposes SO3, R symmetry, and SO2, and then after topological twist, this 3 scalar becomes the one form after top. And if you combine the gauge group and then this one form field, one can have the complexified gauge field. That it will give you the complex Chern-Simons, complexified gauge field in Chern-Simons theory. Okay. Any question at this moment? If not, let me move on. So as I mentioned in the previous case, so here, so the theory 3n equal 2 theory living on this space is labeled by M3. And sometimes it admits a Lagrange description, and generically it doesn't have a Lagrange description. Let's look at the particular case which admits the Lagrange description. So the simplest example one can consider for M3 is just a very simple product space, S1 cross sigma G. Sigma G is the Riemann surface of genus G. So in this case, M5 brane living on the compact fund on sigma G is so-called class S theory. I think most of the audience are familiar with this construction by Gaiotto. And then, so therefore, if you compact find a class S theory on S1, class S theory for the n equal to 2, which has the H supercharges, because holonomy just reduces the SO3 to SO2 on the sigma 2. Okay, so therefore it has a therefore the reduction on class S and on S1 will give you 3D n equal to 4 theory. For instance, sigma G admits the so-called Pantz decomposition, and depending on Pantz decomposition, one can have this kind of diagram for class S theory. So I mean, if you have the just cutting on the Riemann surface like this way, corresponding to assigning gauge group like this. But in generally for higher rank, this kind of diagram doesn't have admit the Lagrangian description. However, if you go to the 3D n equal to 4, one can have the mirror symmetry. So if you take a mirror symmetry of this space, indeed it has admit the Lagrangian description, which is very simple. So you have an n gauge, U n gauge group, and G at the joint hypermodulus. So that's the description of the T of M3. So this is T of M3, where M3 is just product space here. Okay, so one can slightly generalize this construction by, so this is just product space, but one can have the total space is just S1 fibration over sigma G, and whose first chunk number is indeed P. So this is called, let's see, S1 bundle and total space on the sigma G. So this is total space is called OP bundle. over sigma g. So slightly, you just fibering S1 over the sigma g. So then the holonomy becomes SO3 now. Therefore, the theory becomes 3D n equal to 2 instead of n equal to 4. It breaks the half symmetry supersymmetry. Okay. Then the description is simple. In fact, this the fibration by first Chern class with equal to P is introduced in 3D n equal to Chern level P. And then the other multiplet are just decomposition from here to here to 3D n equal to 4 to 3D n equal to 2. So therefore, 3D n equal to 4 vector multiplet is just a n equal to 2 vector multiplet and 1 adjoint chiral, 3D n equal to, and then 1 hyper multiplet, adjoint hyper becomes 2 adjoint chiral. So therefore, in total, you have a 3G adjoint chiral and then level P Chern-Simons, 3D n equal to Chern-Simons. That's the Lagrangian description of this. Once you put the M5 on this 3 manifold, you get this kind of Lagrangian description. Any question at this moment?
Satoshi, there's
yes,
a question in the chat.
Okay, let's see. Let me take a look. Is there an easy way to see there's no Lagrangian description? Easy way to see. No, I mean, I don't have any good answer, but that's just expectation. I mean, if you put the theory living on Riemann surface with the generic, and I mean, class theory generically do not admit the Lagrangian description. Since the 3 manifold is much more complicated than the Riemann surface, generic 3 manifold does not admit the Lagrangian description. That's just a expectation. I don't have a good explanation why it doesn't admit the Lagrangian. There may be a way to cook up Lagrangian, but I don't know. Okay, that's the, yeah.
So I also have a related question.
Go ahead.
So for the 3D n equals to 2 case,
yes.
So why is there a Lagrangian description? So could you have a non-Lagrangian 3D n equals to 2 construction from that?
I mean, you in this space, you mean, or generically?
Yes, in that space or generic.
Yeah, generically, so as I mentioned, so I don't see I don't have any general prescription to find a Lagrangian. But here in this space, it's a simple operation. There are lots of evidence to that if you compact find this space, the theory become like this. That's I can also show you why this is we can just tell this is a Lagrangian description of this is M3. But as I mentioned, I don't see any reason to find the Lagrangian for generic manifold M3. Does that answer to my question?
Yeah, and also for the notion of non-Lagrangian, does it mean that something like just a strongly coupled gauge theory in the IR or something like that?
Yes.
Okay, just a strongly coupled theory.
Yes. Any other questions?
So I have a question here. So this 3D n equal 2 theory, if I turn this level p equals 0, it will automatically become an equal 4 theory?
Yeah. So just enhance to me here.
Okay, thank you.
Yeah. Any other questions? Okay, let me move on. So the simple setup, so since we know that it's kind of like a good setup, why not use this good setup to find some like a duality between the duality. So this is the for instance, the simple setup is the so-called if you consider the space is the total space is the cotangent of length space times S1 times cotangent of sigma G. Okay. Then one can just wrap the M5 branes on the length space times S1 cross sigma G. And then, so if you look at the theory compact from sigma G, then the class S theory living on here. On the other hand, we know, so the length space LP1 is indeed just a G equal to 0 and okay, sorry, so I think I should use this one. Length space LP1 is just G equals 0 version of this bundle. Okay, so therefore here, if you compactify theory on here, the theory compactify M5 on length space, the theory living on here is just a 3n equal 2 theory and one vector output or one adjoint kernel and level P Chern-Simons. Okay. And here, so we know the machinery to compute the so-called partition function on the both side. So here, if here it just you can just compute so-called index. This is S1 cross length space P1. It's just the index of this class F theory. In particular, if you want to see the duality, it's we just need to look at the so-called Coulomb branch index of this theory living on here. On the other hand, so that we know that how to compute the partition functions S1 cross sigma G, sometimes it's called equivalent Verlinde formula, or sometimes called twisted index, or some more precisely a twisted index. And then the organizer of this seminar is an expert at computing this a twisted index. So one can compare these two objects. So that if you compute the Coulomb branch index of this space, and if you compute the A2C index of this state, in particular, this A2C index is indeed the so-called computed by so-called sum over beta vector, and XP is indeed so-called give you so-called fibering operator, and then this is called fibering. I forgot which one is. Which one is called fibering operator, and then this is gluing operator. I forgot. I think this is fibering operator, and this is gluing operator.
Yeah, I think HSO to 1 minus J is gluing operator.
Yeah. And then this is very particular, very similar to what we saw in this Witten-Rishkin-Turaev theory, that if you put the theory on S1 cross sigma G in Chern-Simons, you have a T to the P S to S lambda 0, lambda 1 minus G, sum over lambda. So this is Chern-Simons invariance on the S1 cross sigma G. So which is the situation is slightly different, but essentially the philosophy is the same. And then in fact, so this partition function admits the so-called very geometric interpretation that this is the so-called graded dimension of the holomorphic section over the holomorphic section of so-called determinant. L is called determinant line bundle over Hitchin modular space of sigma G. Of course, the gauge group or structure group G is coming from here. So therefore, U, GL and G. And C. Okay, so this is called the graded dimension of this holomorphic section. It can be understood. So therefore, it should be all if you look at the constant in front of T, in fact, everything all the positive constant. And let me show you the computation. I will stop sharing the slide, and then try to share the mathematical. Let's see. Let me. Okay. So if you go to the archive of this paper, there is a so-called the mathematical file is attached, and they compute so-called Coulomb branch index. Coulomb branch index, And then, so this is the genus 2 case and genus 3 case. Sigma G is the G is equal to 2 and G equals 3. And they just showed us something called when G equal to 2 and the P length space P is equal to 1. So this is P equal to 1, P equal to 2, and P equals 3. So this is the computation of the length space index. Okay. And then here, so they use TQFT technique to compute the so-called twist index. But I can just show you that there's another way to so-called sum over beta vacuum. What was it? Yesterday I computed. Good. Okay. So this is called beta equation. So you can see my screen, right? No.
Yeah, I can see.
Okay.
I think.
So this is the beta Anderson equation one has to solve. And then this is a so-called Hessian. And then this is, sorry, I should call K P instead of K, sorry. And if you compute the partition function A twist index like this way, here you have the, you can compare these two, for instance. Let's see. So if you, this is level 1 genus 2. If you want to compute level 1 genus 2, let me compute. No, I hope it doesn't take so much time. Here you go. So this is the genus 2 and the K equal to 1. So that match with this guy. And for instance, here genus 2 level 2. So genus 2 level 2. If you try to compute this, oh, I already computed. So this genus 2 level 2 is this guy, and then Coulomb branch index this one. So one can check. This is indeed they coincide, and as you can easily see, all the coefficients are positive. So therefore, this indeed counts the number of homomorphic section or determinant line bundle over the Hitchin modular space. Okay. Let me stop sharing and then go back to the slides. Oops, just a moment. I hope. Okay, so this is one of the very successful example of 3D correspondence. And here, just be careful that you have to always include this, how to say, Kaluza-Klein model to S1 to see the equivalence of partition function. Okay. Okay. For hyperbolic manifold, I think this seminar series already talk about the so-called hyperbolic manifold of three hyperbolic structure and three manifold and so on. The most of the three manifold admit the hyperbolic like complete hyperbolic metric structure. And then this hyperbolic manifold, three manifold admit so-called ideal tetrahedral triangulation. So here, as you know, I think most of people already knew that so if you consider upper half plane and you just consider usual story.
Satoshi.
Yes.
There's a question from Professor Wu in chat.
Yeah. I wonder why we have karma since equal. Oh, okay. So here, okay, when p equals to 0 case, you have the there is no adjoint hyper, but you have one 3D n equal to 4 vector multiple. The 3D n equal to 4 vector multiple decompose into one 3D n equal to 2 vector multiple, one adjoint chiral. So you have one adjoint chiral. Do you understand what I mean? So let me write that maybe. Let me write here by rect 3D n equal to 4 vector multiple is equal to 3D n equal to 2 vector multiple plus adjoint chiral. So therefore, we n equal to 2 language, you have one adjoint chiral that appear in here. Is it okay? Okay, good. Okay. So So I think this seminar series already talk about the hyperbolic structure and so on. So I don't think I'm not going to detail, but here you can just consider the upper half plane in three-dimensional space, and you just consider dx squared plus dy squared plus dz squared divided by z. So this is a hyperbolic metric on the upper half plane. And then you just consider this, how to say, geodesic in terms of this hypermetric. One can have the ideal tetrahedron that is characterized by so-called this the complex number z, or the position 0, 1, z. And this z, once you specify z, the other part is automatically determined. For instance, angle z, this is argument of z. And here you have a z prime and z double prime are related by 1 over 1 minus z, and z prime is 1 minus z inverse, and so on. And then I think I didn't write down the name. So this is the famous story by DGG, Timofey Gayatokukov, that so if you consider, one can consider the theory leaving T of this ideal tetrahedral space. This is indeed 3D n equal to 2 chiral multiplet, free chiral multiplet, and the U1 flavor symmetry with -1/2 Chern-Simons level. And if you consider the so-called a three partition function of this T of I'd say ideal tetrahedral theory, one can have so-called quantum dialog. And then, yeah, quantum dialog, so whose definition is given by here. And then to try to construct M3 from the ideal tetrahedron, one has to glue the ideal tetrahedron by just imposing this condition at the edges. So in fact, in order to glue the tetrahedron, the total angle has to be 2 pi. So therefore, pi I, sorry. Is it 2 pi? 2 pi? I forgot. Yeah, 2 pi I. So therefore, this condition is indeed imposing so-called the gluing tetrahedron is introducing so-called superpotential. In fact, and if this condition indeed amounts to the R charge of all the chiral multiplet is equal to 2. So therefore, one can introduce so-called superpotential. And potentially, one can gauge in this U1 flavor symmetry. And the typical example is that this 2-3 Pachner move in this ideal tetrahedron hyperbolic space can be understood is a very, very basic example of the duality of the 3n equal to 2 theory. So one is the 3n equal to SQED with NF is equal to 1. You have the chiral and anti-chiral with charge plus minus 1. And since you have a U1 vector multiplier, you have to integrate over the sigma. And then on the other hand, you have a so-called 3XYZ model is so-called 3 chiral multiplet with superpotential this guy. Okay. So this XY, so this 3 decomposition corresponds to XYZ, and this upper and the lower ideal tetrahedron can be understood as the chiral multiplet, anti-chiral multiplet here. And then if you just follow the owner machinery supersymmetrical localization, the partition function or identity of partition function amounts to the so-called equivalence of the quantum dialog identity becomes identity. So in this way, so by using this green procedure, one can construct a partition function of T of M3 theory for hyperbolic manifold M3. In fact, I just only write down the Squash 3 sphere, but one can also consider S1 cross S2. And there is a corresponding building block for length space, not length space, sorry. This identity heterohedron, which is DGG2. Timofey Gayatov's second paper is written, but due to the space of my slide, I didn't write it down, and which is extensively studied in the past years. However, there is a caveat of this construction. If you use this construction, it only picks so-called the non-abelian flat connection. As you know, I think this seminar series already introduced the equation motion of Chern-Simons theory. Chern-Simons theory, the equation motion, of course, the flat connection. And then this is the classical solution. And of course, once you try to consider quantum theory, one has to consider the fluctuation from this flat connection. And then, in fact, if you want to consider all the dynamics from M5, and one has to include all the contribution from this flat connection. But in this construction, the caveat is only capture so-called non-abelian flat connection, but this construction miss abelian flat connection. So therefore, it only captures subsector of this fibrant system. So that was the caveat of this construction. So the reason that here it's you just decompose the three manifold in this very singular space. It's a very singular. It cannot be called manifold, right? Because it's a it has some singular pointer like this way, and gluing this like a very singular space, and to make it the ordinary like a smooth manifold, somehow we miss something, and then what we miss is abelian flat connection, and that is actually indeed crucial in the later construction. Any question at this moment? Can I move on in that case? Okay, before moving on to the so this generic the construction which capture abelian connection, I'd like to talk about so-called SL2Z transformation in the both Chern-Simons theory and then 3n equal to 2 theory. Both transformation was given in the by Witten. So this construction is given by the famous Walker and then Jones polynomial Witten, and this one is I think around 2000. So both have SL2Z transformation. Let's first let's follow the historical order. SL2Z transformation in Chern-Simons theory is just the theory SL2Z transformation in West-Zumino-Witten model. Because if you consider the Chern-Simons theory on a torus, there is a Hilbert space living on torus, and then there is a mapping cross group action acts on SL2Z on a states living on torus. That is what we can consider. In particular, so this S transformation corresponding to so-called Hopf-Link invariance. And T transformation is very simple. You just have so-called framing. You just introduce so-called some twist on a knot. That is called T transformation. Even though topologically they are equivalent, but in Chern-Simons theory, it introduced some very simple but non-trivial operation. Very simple. You just have so-called framing factor into you have to include Q to some power. That corresponds to T transformation is West-Zumino-Witten model or Chern-Simons, whichever call it. On the other hand, 3-2 case, the S transformation is given by you just have a background gauge field, and you just gauge it background gauge field to the XZ. You just gauge it. You just gauge it like this way. And they introduce so-called mixed Chern-Simons term, where they introduce another background gauge field X1. Okay. And in particular, so this construction, if you just translate this transformation in terms of partition function, you have this so-called background gauge field or flavor symmetry, whichever you call it. X2, you just gauge it. So you have to integrate over, and you just introduce so-called S term or like a mixed Chern-Simons term like this. This is in fact equivalent to the, if you look at the not invariance in Chern-Simons theory, you just start with so-called unknot. So this is the just ordinary cupel hammer, and this is called unknot invariance. And you just gauging corresponding to this this R2 is so-called color. So you just sum over all possible color between 0 to R2 and just introduce this kind of framing factor. And this is exactly the same as the 3D equal to S transformation. So likewise, T transformation is just introduce so-called the Chern-Simons term on background gauge field. This is indeed includes some set of function in the index of 3D equal to theory, but that is equivalent to the just including so-called twist in the not invariance in Chern-Simons theory. You just adding this framing factor is equivalent to this introduced set of function in the 3D equal to theory. So there's a beautiful match between SL2Z transformation between 3D equal to theory and Chern-Simons theory. Any question at this moment?
Can I ask you a question? So,
sure, go ahead.
So when you discuss the abelian connection in your last slide, do you mean the abelian connection for the Chern-Simons theory rather than the 3D equal to gauge theory? I think from the perspective of gauge theory, nothing is missing, right? So,
I'm sorry, from the perspective of gauge theory?
So when you discuss when you said that CD correspondence data cover the abelian connection, do you mean is this abelian connection is for the Chern-Simons theory?
Yes, in Chern-Simons theory. Yes.
So the 3D into gauge theory, so from the gauge theory perspective, nothing is missing, right? So
no, I mean it missed something. So for instance, if you take for instance, h bar goes to 0 limit or b square goes to 0 limit, you have an e to the usual like whatever w tilde. This is called in physics language twisted potential. In the quantum topology language, this is called normal Zaghian functions. And this twisted how to say superpotential miss abelian Flood connection. So we miss something, even gauge theory.
What's the abelian connection for the gauge theory? Sorry.
That is, I'm going to talk about later.
I see.
Okay.
Thanks.
Yeah. Any other questions? Okay, so let's try to construct the partition 3 angles, two partition functions which capture both abelian and non-abelian function. But before that, let's recall that the generic construction of 3 manifold by using surgery.
There's a question in the chat.
Okay, is the gauge connection A T trans a U1 connection? If so, is it properly normalized in T transformation? Yeah, here we assume the connection. Here is just the background gauge field U1. Yeah, that's true. If so, is it properly normalized? I don't understand the meaning of what do you mean by properly normalized? So here the connection, all connection is the U1, independent of background or gauge field. We just consider a U1 gauge field. I don't understand the meaning. Okay, should be multiplied by 2 pi z. That's true. That's true. So here you just level one. Level one. I think I don't know. Or maybe. Is that a true? I think level should be 1. It's just level. Yeah. I think the normalization here is the opposite. I think I made a mistake somewhere. Sorry. I think I copy and paste from somewhere else. The other normalization, that's why 2 pi and 4 pi is a difference. Sorry. Level 1. And does it answer the question? Oh, okay. Okay. Good. 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 Okay. So let me move on. So instead of just constructing 3 manifold by ID the tetrahedra, so we can do a bit more like a smooth way to construct M3, which is called surgery. So there's a big theorem in low-dimensional topology by Lee Gresham Wallace, also and also Kirby. The great low-dimensional topologist. So every 3 manifold can be constructed in so-called integral dense surgery on the link K inside S3. So dense surgery, most of people already understood. You just put the link inside S3 and they just remove the so-called tubular neighborhood of the link. Tubular neighborhood just thicken the link component. And this is red part is the tubular neighborhood. It just removes around the link component. That is called S3, get rid of K. And of course, the boundary of this link complement, this is called link complement, is a torus. So one can just glue the solid torus back to the link complement. However, just bring the solid torus back to the link component. There is freedom freedom to choose, because I mean a mapping class group on torus is SL2Z. So therefore, if you glue both the boundary is torus, so therefore one can just glue the both torus by using the SL2Z action. That is called the dense surgery. And when P of R is usually a rational number, but if this number is the integral integer number, it's called integral dense surgery. And generically, it's just rational. And in particular, so one can just consider the link is just bunch of component of the bunch of unknown, which is like this way. And this A1, A2, A3 is just a number here. So the A1 0, so just AI 0, and then you just make it SL2Z. So this is all positive integer. So that is called Kirby diagram. And this diagram will specify 3 manifold by using this integral dense surgery. So this is the just given this diagram, one can just construct so-called graph. And also one can construct the so-called adjacent matrix or linking matrix, whose diagonal component is just this framing number. Yeah, this is called framing number. So integral framing number, diagonal entry is A1, A2, A3, and so on. And then of diagonal is if there's an edge, you should put the 1 here and 1 here. And if there's no edge, you should put the 0 here. If that is so, given this Kirby diagram or graph, one can construct the symmetric matrix, which I call it Q. And this construction, so given M3, I mean, given the link K, one can construct M3. But it's not unique procedure. There is another way, another link K prime, which gives the same M3. And this the relation between K and K prime is given by so-called Kirby map. So this is usually not the standard copy move, but I think this is a different way of.
时间到了，能听得到、看得见吗？
Oh, it's already time's up.
能不能听见？
时间到了。
Yes.
今天同样的，我会过一会儿，我会把就是在我们会议里面的这个人的名单
Sorry,
会导
there.
这个会作为我们考据的
Or
一个
maybe
意
I
见。
should mute him.
好，那么我们在星期二的时候给大家讲过，
Just
就
Yeah.
传案。
okay.
Yeah.
Okay.
All right.
So so-called copy normal move. So this copy given the copy diagram, so its construction is not unique, and the relation between the diagram which gives the same M3 is given summarized these moves. So you just add one more dot here or one unknown component, and then plus minus increase the or decrease the framing number like this way. Or you can add another unknown among two vertices, and then increase like this. Anyway, so this is a standard procedure. Those procedure will give rise to the same M3. And then the last one is just if you have a disjoint graph like this way, one can connect by adding one unknown here, and just connect like this, and they put the 0 here. And that both will give you the same 3 manifold, independent of A, surprisingly. That is the operation that will give rise to the same M3. Any question at this moment?
Sorry, I have a little bit. I have a little bit of question. So how
Yes.
does Kirby-Neumann move affect the surgery you mentioned in the last page? How does this influence this dense surgery or reflect in this dense surgery procedure?
No, I mean here, so you have the whatever. So for instance, this one, this diagram. Okay, let me write down the explicitly. For instance, if you look at this diagram, you have the A1. So you have like this way. Anyway, so I'm not gonna write down everything.
Okay.
Anyway, I'm not gonna. So this is A1 framing, A2 framing. This is a part of the Kirby diagram, but even if you introduce some other components, something I call it the brew, and then the original one is something
I
like
see.
whatever, original one like this way. Anyway, anyway. So this is A1 plus 1 maybe, and then here you put the plus 1, and then A2 plus 1. Even if you include this blue one, and it performs the dense surgery, the resulting 3 manifold is the same. That's what you mean.
I see. And this framing A1, A2 is this framing is the same as the framing you mentioned previously. I mean.
Yeah. This framing. Okay. Yeah. Of course, the framing means. I think what you mean by this guy, right?
Yeah. This guy.
Yeah, it's the same thing.
Yeah.
It's the same thing.
Oh. Okay. Thanks.
Okay, so then if you consider the space of 3 manifolds, I mean, 3 manifolds are very rich, as you know. I mean, people study 100 years of this 3 manifold, and then this is called this construction. The 3 manifold construct of this Kirby diagram is called plumbing 3 manifold, which is actually, I wouldn't say it's actually it covers many 3 manifold, but not all, of course. So this I call it sigma PRS is called Priscon 3 sphere. Whose definition I didn't write a definition, so let me write down definition. The sigma PRS is just you just consider the S5 and then intersect with Z1 P plus Z2R plus Z3S is equal to 0. And I treat this Z1, Z2, Z3 is the complex variable. So therefore it's inside a C3 inside of C3, there is a S5 unit sphere, sorry, C3. And you just look at the intersection between unit sphere in C3 and this equation, also the complex codimension 1 manifold in here, then one can obtain the so-called Briscoe 3 sphere. And that is the inside a so-called cipher manifold, and cipher manifold essentially admits, roughly speaking, just S1 bundle over M3 over some Riemann surface, roughly speaking. But there is it admits the singular fiber and so on. And the priming manifold coming from this Kirby diagram is much bigger than cipher manifold, but not all. So they're all. So there's a huge space which cannot be covered by plumbing manifold. Okay, with this preparation, one can construct so-called Z-hat invariants. Any other question at this moment?
So for this more general manifold,
yes,
can they be described by like some kind of three-dimensional link of some other kind of complex singularity?
Complex singularity. I think this kind of
in general, like four-dimensional singular cone, you know. So the three manifold is a link of that cone.
I think those are only algebraic, so therefore it's inside of priming manifold M3. That's I would imagine. So those algebraic one is just all fits into the priming 3 manifold.
Oh, okay.
Yeah. And then, so this generic, to get this generic 3 manifold instead of this unknown. So this is I only use unknown right here. And the integral surgery, and I just consider three diagram. But to get the generic 3 manifold, one has to use the generic link instead of unknown. Here only I am consider unknown, but here you have non-trivial unknown, right? So therefore, anyway, that's how you construct the generic 3 manifold.
Okay. So
yeah.
I just wonder whether you have some kind of like more general singularity that you can generalize this hypersurface equation, right?
Yeah, hypersurface equation. Yeah, that's true.
New singularities.
That's
new
true.
three manifold.
That's true. So, but then I would imagine that everything fits in Plum 3 manifold because everything algebraic. Yeah.
Yes.
This construction. Yeah. So this algebraic construction all fits into the Plum manifold. That's what I would think. Any other questions? Okay, let me move on. So I'm going to talk about Z-hat invariance, but Z-hat invariance for this 3 manifold constructive Kirby diagram. So, and in particular, I will consider only the G is equal to SL2C, SU2 or SL2C. For generic case, SL2C is constructed by Gukov-Putrov-Baffa and Gukov-Pei-Putrov-Baffa. For higher rank, A-type gauge group is so-called S-Park. It will give a definition of for priming manifold. For at least A-type, the construction of this partition function is for priming manifold is at least known. Okay, so the prescription is very simple. So given the vertex of planning manifold, so the vertex is this one, you assign the x minus 1 x inverse square, and with some framing factor, aj is just a really framing number here, and just some rational number. And then if you have edges, so like this way, so this is I and j, you have edges, you have the this part xi minus 1 over xi. This can be understood kind of like adjoint chiral field. And adjoint chiral field xj minus minus xj inverse. This can be understood so-called gauge field coming from this for 3D angle 2 theory. And this part can be understood Z3D. So as you recall, so the 3D n equal to 2 theory living on R cross CQ. So there's 3 dimension, but there's a boundary on CQ. The boundary is in fact in 2-dimensional, and this part can be understood as a 2-dimensional partition function. So therefore, this can be understood as the 3D 2D couple system, where this boundary contribution is coming from so-called it's a boundary condition at the infinity of the 3D space, the spatial infinity times time. And this 2D partition function is the so-called generalized theta function. And essentially, what we have is just Q is the adjacent matrix or linking matrix I constructed from this plumbing graph. And then you have so-called quadratic term for Q, and you just multiply xi times some integer. And this B, in fact, is the so-called kernel of Q, is indeed so-called spin C connection, spin C structure M3, or more simpler language, this can be understood H1 of M3, which is the of Z, which can be understood as divided by some discrete gauge, let's go n times some power, discrete abelian group, depending on the plumbing graph. So this can be understood as the abelian Flood connection of M3. So this B essentially label abelian Flood connection of 3 manifold, or more precisely spin C Flood connection, more precisely. So here, so this partition function B is labeled by abelian Flood connection M3. So therefore, it automatically encodes the information abelian. So that by definition, okay. And if you compute this one, so this is just a ordinary integral. So this computation is given by just ordinary. Just look at the residue at 0. And so therefore, essentially what you need to do is just do the computation of this one is just look at the all gauge invariant part. The gauge invariant part means the term which is independent of xi. And if you do this integral, what you have is called the Q series. So Q to some power, which delta is some rational number. But if you just factor out this Q to some power delta, everything becomes the integer power and then some integer coefficient. So I think, sorry, not integer power, it's a natural number. So natural number, that is actually a very good sign of, I mean, of course, it counts so-called BPS states of 3D n equal 2 theory. So therefore, this is actually indeed natural. So this can be understood, this number is the graded dimension up to -1 to the f of the graded dimension of the BPS number of 3D n equal 2 theory. And in particular, so this Z hat converges at the unit disk of Q. So now I treat Q as the essentially C subvariable, and it converges in the unit disk. And furthermore, it invariant under the Kirby-Norman moves. So which means that if you have a 2 diagram which is related to Kirby-Norman move, and if you compute Z hat, then you get the same number, same Q series. Any other question at this moment? Any questions at this moment? Okay, let me give you the some stop sharing and then show you some computation of this invariant. Let's see. I don't remember which one will compute. Oh, this one. Okay, so here is the computation of this z-hat invariance. So for instance, you have this is priming diagram, and you just specify the Fleming number like this way, and this will give you so-called Briscoe sphere 237. And then you just do the computation, and at the end of the day, you have this Q series. As you can see, everything integer power, and then after factor out Q to some rational number. And since here, this Briscoe sphere has only one abelian Flood connection, which is trivial Flood connection. You have only one Q series. And then let's see, did I open the, no. And the Kirby invariance on Kirby mood, for instance, one can do this, the following stuff. So if you consider the cipher manifold, this is just a name, how to call the cipher manifold. One can just construct from this priming graph and then do the computation. It has a lot of abelian connection. So therefore you have a 1, 2, 3, 4, 5 abelian connections. So you have a 5 Q series. This is actually corresponding for instance, B0, B1, B2, B3, B4. And for instance, one can just perform the Kirby move of this priming diagram. I don't think one can remember, but let me copy and paste. I think here I performed the Kirby diagram. So this is Kirby move 1. I just, I think if you recall, you just add -1 to the original diagram and it put the additional diagram and do the computation. At the end of the day, you get this Q series, and this one is, oh my goodness, this is the same as original Q series. That's the Kirby move 1, and Kirby move 2 is just include additional vertices in the original diagram and change ±1 in the adjacent vertex, and they do the computation. You can just again see that the Q3 does not change like this way. And then you can do the same thing for Kirby 3 and so on. I mean, I'm not going to repeat that one, but this is the SL2 case. Yeah, and you can see the Q3s and z-hat invariance. Okay, I will stop sharing and then move back to the iPad. Sorry, I'm going back and forth. Okay. Okay, now going back to, and then what is the connection to complex Chern-Simons there? So to get the complex Chern-Simons invariance, one has to sum over all the abelian Flood connection. Oh my goodness, it doesn't work. I don't know why. Oh, sorry, I think there's something wrong on my iPad. Anyway. Oh my goodness, sorry. I think somehow can you see my, I think, oh, okay, now you can see. So this is z-hat invariant, and B is abelian Flood connection or spin C structure of a 3 manifold. You have to sum over all possible abelian Flood connection with some weight. With some matrix F. I'm not going to give a definition. It's just a matrix defined coming from so-called linking number of abelian function. I'm not going to explain. So you can just look at if you want to know the definition, you can just take a look at this paper, GPPV, some matrix, and then weighted by some original classical Chern-Simons action of the abelian Flood connection. And then what's remarkable is that if you take the so-called radial limit of this invariant, radial limit, I mean, the Q is just approach from the origin to the root of unity, which is e to the 2 pi I k, where k is integer. K is just a shifted level of the Chern-Simons level. And if you take a latest limit, this will reduce the so-called Witten-Rishkin interrupt invariance of M3, usual M3. So here is the ordinary root of unity in Chern-Simons theory, Chern-Simons theory. But here we need to be careful where you take a limit. It's only linear limit. If you take the different limit, you get the different value. Okay. And in particular, when you take the K goes to infinity, so this admits so-called, this is the original Witten's paper, admits so-called asymptotical expanding conjecture that you have the A is labeled by the flat connection, and then you have this perturbative expansion with respect to the level of the Chern-Simons term. And from going back from this original Witten's asymptotic conjecture of the Chern-Simons invariance to the back to the this complex Chern-Simons invariance, this one has to perform so-called resurgence. Okay. And then so that which I'm going to explain. And then for instance, the M3 is a length space, let's see, L51, which can be just obtained from just dot with depends on plus minus 5. The Kirby diagram is super simple. This dot with framing number plus minus 5, and then it has the of course the abelian flat connection. The flat connection is V5. Pi anyway. V5, and then V5. So one has to modeling out the Y group action. So the Z hat is the three of them in general. And then everything is written by monomial of Q. And then S matrix here is given by 3 by 3 matrix like written here. So the Chern-Simons complex Chern-Simons invariant of the length space is super simple. But once you take the root of unity, one reduces to so-called usual Witten-Rishkin drive invariance of the 3 manifold length space. And the reason why I put the question mark here is that this is only given in plumbing manifold so far. And we don't know the generic definition of complex Chern-Simons invariance. And then since there's Korea defined its Chern-Simons invariance, and this WRT is indeed as it can be defined so-called modular tensor category of the modular tensor category, but the modular tensor category has so-called Okunian rigidity, which means that there's no deform. You cannot deform the modular tensor category. But here, complex Chern-Simons theory should be defined a generic Q, or like for instance, root of the unit disk. So therefore, Q can be deformed anywhere, right? Like this anyway. So therefore, we need to define the complex Chern-Simons theory. We really need a new formalism to define the so-called TQFT. So-called, of course, the quotation mark of TQFT. And most likely, we need to use spin C structure, and the formulation of a complex Chern-Simons theory on the rigorous mathematics is the open problem at this moment. So far we have some example of the plumbing graph, which has a candidate of complex Chern-Simons theory, but mathematically to define the complex Chern-Simons invariance is still open. To confirm, can negative integer appear in Q expansion? Yes, of course. I think so. Of course, it's a trace of -1 to the F Q to the J over 2 minus R plus minus depending on notation. This is the index of 3n equal to 2. So therefore, since -1 to the F, there's a Fermat contribution. It can have the here you can have negative integer. Okay, does Kirby moves change the number of abelian flat connection? Of course not. So the abelian flat connection of three manifold. So therefore, if the three manifold does not change, the number of Flood function does not change. Abelian Flood function does not change. So okay. Any other questions? Okay, so to go beyond the plumbing three manifold, one has to define the so-called or link component z hat. This z hat for link component, and the candidate was given by Gukochman and Lesk, and then the prescription one way to obtain this z hat for not link component is just doing so-called resurgence. I'm going to talk about, I think 15 minutes has been left, so, but I'm not sure if I can go into the detail, but let me go. So just start with the Jones polynomial, which in the n is a color, k is a link, q is just an ordinary q, and take the asymptotic large color asymptotic expansion. N goes to infinity, h bar goes to 0. This is usual volume. Usually, we will do the volume conjecture, and then this admits so-called this kind of expansion. This kind of expansion, h bar expansion, where this denominator is called so-called Alexander polynomial, and then here the p are some polynomial in terms of x, and this is called Melvin Morton Rosansky, as far as I recall, the expansion. And if you do the Borel resummation of this logical asymptotic, one can obtain so-called the complement of the z hat for link complement. And here z hat of the link component labeled by again the abelian Flood connection of the link component. In this case, actually not component. So there is only one component in the link, which is called not. And in that case, everything labeled by b, which is integer. And you just do the generating function of z hat, which is called f of k. And in particular, some example of f of k is known. For instance, this is called trefoil. Trefoil is, as I'm very familiar to write down this is trefoil, and the figure 8 is this one, this note. Anyway, so this kind of note, the expression is known, and then it can be written in terms of Q4 hammer like this way and like this way, and which is very closely related to, I mean, most of people here are not familiar with, but the so-called Habiro's cyclotomic expansions. It's a very close relation between Habiro's cyclotomic expansion and this FK invariant. And one can perform so-called surgery of this surgery of the link invariant will give you cross ring manifold. And then this surgery can be understood as so-called this integral. This integral, for instance, this can be under this factor x to the 1 minus, I mean, p over r surgery over k amounts to the solid torus contribution, and then link component in contribution, and then last one is the green contribution. And if you perform this integral, one can obtain the z hat of the cross manifold, which is just a Dehn surgery of the link component. Okay, so it's a good, and in fact, this integral is in amounts to the, you just replace this x, some power of x into the some q to the some power. That is called so-called Laplace transformation. And let me show you one thing by Mathematica, by performing the Laplace transformation. Let me again stop sharing and show you the Mathematica. Express computation, physicists like express computation. So let me show you the So here, Laplace transformation is just replace x to the some power to the q to the some power. And this f is called is the f of k I introduced in the slides, and the st is the actually the torus st torus knot complement and the xq. And for instance, if you start with the trefoil and do the integral one surgery, what you get is the so-called Briscoe 237 sphere, and this is the Q series. And if you have a good memory of this good memory, did I close already? Yeah. If you have a good memory, this coincides this one. So as you can, if you compare with this one, so this is surgery of the FK trefoil, and this one is the coming from the Kirby move and Kirby diagram. And as you can easily see, up to some, yeah, no, there's no up to. So the Q3 is coincided with this one. Okay. So the level, so framing one surgery of the trefoil complement will give you Briscoe 237, which is the another way to construct is this one. So therefore, this prescription, I mean, of course, the construction is just give you the same answer, and so on. So one can do the lots of surgery, and you get the other manifold, and you can obtain lots of Q series and so on by performing this integral. So okay, that is consistent with this Kirby diagram construction. Okay.
Satoshi, there's a question.
Just a moment. Let's see. Just want to let question in the chat. But in the example L, you shown us it looks a number of B do not match. Oh, okay. In fact, so the example here and here, as I mentioned, so spin C structure of M3 is indeed equal to H1 of M3 dot Z divided by Z2. Sorry, I think H1 M3 Z divided by Z2. Z2 is a wire group action. So now you have the Floch connection, abelian Floch connection for length space is Z5 divided by Z2, but as a set. Then 1, 2, 3, 4, 5, and it just identified like this way by Z2 action as a set. And what's left is Z3. So therefore, Z3 is given correspond to this set. Do you understand? And then length space, depending on 3 manifold. Okay, good. So therefore, you have a 3 by 3 metric. Okay. So therefore, so this construction by not complement, I mean, in fact, so this is one way to construct, but I mean, some not complement depending on the, I mean, the construction definition and construction. I mean, rigorous definition is, I think at the mathematical rigorous level, I think no. I think that's I maybe Sergey may disagree. Maybe I said wrong. But I think still a lot of things one has to, the formulation of this FK, one has to study a lot. That's my understanding. Any question at this moment? Okay.
Excuse me,
Yes,
I have a question. So
yes.
in this J, so
Yes.
what's this delta K and the P1, P2 related to the link K, the node K?
Oh, okay. So this delta is called so-called Alexander polynomial of the Alexander polynomial of link. So which has the definition by scaling relation. It's a super simple. I mean, even before John's polynomial, we already knew. Even like early 20th century, we know the definition this delta K, and P1 really depends on the link or not K. So you have to really perform the asymptotic expansion at the large color and to read off Pi. That depends really K. So some polynomial of X. And that appear indeed in this Z hat K. Yeah. Not Z hat K, sorry. The FK, sorry.
So this P1, P2, you can just purely construct geometrically from the link itself, right?
Which one?
There's still this P1, P2.
Yeah, this one, I mean, yes. I mean, in principle, one can obtain it just taking logical limit, one can read off the just expansion by H bar, yeah. In principle, yes.
Thanks.
I think I'm going to skip this one because it's a bit detour of this story. So, but one can construct. There is a very big paper by Witt and 5 brains and not, but there is a connection to the Hattin brains and Witt and construction. But I'm going to skip. Okay, let's talk about the some modularity relation to module forms and resurgence. So as I mentioned, as we see in this Q-series, I explained of this Q-series of Briscoe sphere in Mathematica, which can be obtained by -1 surgery of trefoil of right-handed trefoil, +1 surgery of left-handed trefoil, which I showed just before. And has this kind of Q-series expansion. And then if you show this Q-series to number theorists, they immediately their eye immediately becomes eye open, and which is the which can be written as this form. And in fact, this is f of so-called Q. I mean, it's related to Lagrangian 7th Mach zeta function. In fact, if you F0Q is called a Ramanujan Mach zeta function, and if you plug into Q inverse, one will obtain so-called obtain this Z hat of Briscoe sphere 237. And in fact, this Q inverse of this Mach zeta function is called the fourth zeta function, which has the somehow nice way to construct by using so-called Eichler integral from the familiar zeta function. So familiar zeta function of whatever Jacobi zeta function and so on, it's a generalization which appear in physics is given in this Q to some power, Y to some power, and there's a way to perform some integral to get this fourth zeta function, whose definition is given here. Whose definition is, I mean, it's just Q to some, which means Q to some power, but with particular congress relation between M and R. And this, how to say, this Q-series can be written in terms of sum over all these fourth zeta functions. I think I don't have a time to show the Mathematica. I was planning to show Mathematica by just summing over all psi function to reproduce this Q-series. I'm going to skip. But anyway, so it's magically, it can be written in terms of fourth zeta function. But it's not the magic. There's a reason behind it. That is a relation between modular transformation of this Mach or fourth zeta function and so-called the resurgence. This fourth zeta function, you can consider this can be understand the tau, and this is -1 over tau, whichever. Maybe you can call this is tau and -1 over tau, whichever you call it. This under S transformation of this fourth zeta function have the following properties. This kind of property. usual S matrix of this full set function plus some extra. And this extra can be understood as so-called perturbative expansion. As you can see, 1 over k power can be understood Chern-Simons perturbative expansion. For them, it's just a. On the other hand, the usual piece of the modular transformation can be understood as a non-perturbative part. And as I mentioned, so this d hat is constructed from abelian Flood connection. So therefore, this perturbative series is usually doing a perturbative ordinary quantum field theory way of doing perturbative computation along at the abelian Flood connection, which is of course satisfy the equation of motion. On the other hand, the usual S transformation of modular form, indeed, once you take k is equal to 1, this full set function is just some coefficient times e to some power e power. This indeed is the contribution for non-abelian Flood connection of the Chern-Simons. So this number is indeed the Chern-Simons action on non-abelian Flood connection. And this perturbative contribution can be understood as this perturbative and non-perturbative relation can be understood as the so-called resurgence of complex Chern-Simons theory, which is studied by Witten, and then give explicit construction by this Gukov, Marino, Putrov paper. And this I alpha is perturbative, and it has so-called Stokes phenomenon and so on. If you consider resurgence, I mean, of course, you know, Borella summation and so on, you have, I mean, in fact, I will show you later soon that this part can be, as you can easily see, understood as so-called Borella summation of the perturbative series of Chern-Simons invariants along on the abelian Flood connection. And this extra piece or ordinary modular transformation can be understood as the coming from Stokes phenomenon of this resurgence business. And in particular, as our favorite example, this Briscoe 237 three-sphere, this part can be incorporated into the so-called trigonometric function, sinh and cosh. And if you expand this one, you can, if you expand just to do the Taylor expansion, one can just write down this Borella resummation formula, and then the extra piece is coming from the non-abelian Flood connection, and 237 Briscoe sphere has a 3 non-abelian Flood connection, and then you just do the S transformation of this full set function. For set function, one can obtain non-abelian Flood connection of the 237 Briscoe sphere. So therefore, if you do the modular transformation, one can see the contribution for non-abelian Flood connection in addition to abelian one. Any question at this moment? Okay. Think time is I'm running out of time. So this property is not the usual modular property because you have extra pieces. So this transformation is, any question? Transformation is indeed fits into the so-called quantum modular forms, which is defined by Zagier. So quantum modular form is defined on the actually rational number Q, not the C. So it's only defined at Q, whose X is the taken value of Q. And if you perform this S transformation with, of course, weight K, there is some P of X. And if you take a P modular transformation and then take a difference, and you get some function P of X, which extends of the X can be extends to the function of R with some finite, and just get rid of some finite many point. And this P of X has a nice analyticity property. And this is very vague definition is on purpose by Zagier to incorporate a lot of nice phenomena of this S transformation of the modular transformation, and then of the many like quasi modular form like type behavior. As you can easily see, so if you have a Q of, so this can be understood Q of X, and this is Q of -1 over X. And then if you take a difference, you have a P of X. This can be understood P of X, and whichever you call it. This is maybe Q of X, and this can be understood Q times whatever, -1 over X, and so on. And this has a nice analyticity property, so which is perturbed series. So this phenomena, so magically 237 Z hat invariance showed, and then which is very closely related to so-called Borel relativity summation resurgence phenomena, which is not my expertise, but it's very, very how to say, give you some remarkable interplay between the quantum topology, number theory, and then this how to say, the analysis coming from resurgence. And if you change three manifold here, this quantum modularity, so we expect, or like experts expect, this quantum modular property will hold, even though this Z hat cannot be written in terms of this four-set function. So if you consider the generic three manifold, no longer Z hat can be written at this four-set function or mock modular form. It's more like a higher depth mock modular form, or much more weird modular forms. However, of course, I mean, that's a purpose to incorporate the many function. The purpose of Zagier. So therefore, I mean, here this part is very, very ambiguous. But we expect that all those Z hat fits into this property of quantum modular forms. And then I don't think it's a bit detoured, so that this using quantum modular form, one can reformulate or extend the volume conjecture of the not invariance of like this, but I'm not going to go into detail. So I will stop here. Thank you very much for attention.
Thank you very much. Thank you for the brilliant talk of Satoshi Nawata. And is there any questions from the audience?
Excuse me, I have a question.
Yes.
So in this examples, for example, compute these partition functions and modular forms basically the same partition function is capture. I mean, the partition function of the 3D encode 2 is the same partition function of the 3D complex Chern-Simons, right?
Yes, that's what physicists expect. Yes.
And my question is, is it possible to get this partition function to, in some case, for example, pick some special three manifold such that this partition function can be reinterpreted as some real Chern-Simon, so that is the true TQFT.
So what do you mean real Chern-Simons? It's only, I mean, SU2, for instance, SU2 or something like that?
Yes.
Yeah, this is exactly what I tried to explain. So this ordinary Chern-Simons can be reproduced by taking radial limits from this Z hat or Z, like sum over Z hat. So ordinary Chern-Simons means that the Chern-Simons of this Witten-Rishkin-Turaev sense can be reproduced by just taking radial limit of the Q goes to root of unity.
Okay, I see. So basically, you can use this. I see. Thanks.
Yeah.
The other question is the example you are doing here. For example, the knot complements and Lamy three manifold are all hyperbolic or not hyperbolic, or some of them?
Plumbing is not hyperbolic. I mean, if you have a loop, like for instance, you can have a loop, like a diagram, which usually do not here we do not consider. So we only consider like a tree graph. But if you have a loop, maybe one can have the hyperbolic. I'm not sure. Correct me if I'm wrong. Like if you have a loop, the things are much more complicated. But I'm not gonna go into detail. So if you consider just only how to say the tree type graph of the Kirby diagram, it's not hyperbolic. But if you consider the surgery on link component, one can construct a hyperbolic.
I see.
Yep.
Thanks.
But yes, go ahead.
No, you first. I have some. Okay, I have a question about. So here, these Morph-Force modular form. These example are all involves some sigma PQR -3 manifold. But if you go to, for example, if you go to the Seifert manifold, Plum manifold, it also give you some modular form like this way.
So some, for instance, this is like a, how to say, you have a like a only 3 leg, right? You have a 3 leg. But if you consider like a 4 leg in this Kirby diagram and so on, it becomes it goes higher depth modular form. It's some generalization mock modular form.
I see.
Yes, it's a bit more general version mock modular form. And then if you go to, for instance, hyperbolic manifold and so on, so this kind of modular behavior is not understood yet. But we expect that it fits into this kind of behavior. Yeah, so that's an expectation.
I see.
Yeah.
Any further question from the audience? Oh, there's Kikuchi ask a question in the chat.
What can we learn mathematics for Q3's expansion? For example, what can we draw from the overall power and the coefficient Q to the n? Let me think. Okay, for instance, let's see. Okay, so the equation, for instance, so here we know that this is Q series, right? This is Q series. And if you take the root of unity and the Q equals to infinity, you have this perturbative expansion. And these coefficients can be understood also perturbative invariance of knot or 3 manifold, sorry. 3 manifold, which is radical Vasiliev invariance or Kontsevich, whatever you call it. These are called, this number is also can be understood as the invariance of 3 manifold. So therefore, of course, if you these QCs, these coefficients are related to these coefficients because I mean we just take a limit. So therefore, these can be understood also as a that's an expectation that this number is also will give you some invariance of 3 manifold. That's an expectation. But of course, we need to. Of course, we are doing physics level. So your question, what can we learn mathematically from series expansion? First of all, we don't know the rigorous differential z hat first. We have just an example which behave not very well at this moment. So the definition is missing for z hat invariance for general 3 manifold. And as I mentioned, we don't know how to formulate the complex Chern-Simons theory invariant in terms of whatever TQFT formalism and so on. So that's also open question in mathematics. And then I didn't. So I promised Diego that I tried to mention that his work that he also considered resurgence of this index whatever DGG construction. Actually, he also considered so-called starting from let's see, what was it? Starting from this construction and do the so-called the resurgence to capture the abelian flat connection. That's what Diego and Marcus Marinian's work and Stavros Garafradis' work. And they consider this resurgence instead of this Gukov-Manoresk series and so on. They obtain some other contribution, some other series. So we don't know, we don't understand the other series, what the other series means indeed. So lots of open problem. Okay, if I understand correctly, can you tell what a three manifold is by looking at some of these numbers? Can you tell what a three manifold is? I see. Of course, I mean, of course. I mean, what was it? I forgot. I mean, already we know that we know some duality invariant of three manifold. This will give some number. So therefore, starting computing Z and taking radial limit, one can obtain the duality of three manifold. So it's of course one can tell some three manifold, but depending on given that the invariant that can distinguish all three manifold or not, or classify three manifold, that is totally, I don't know. The question is similar. So given the Chern-Simons invariance, can Chern-Simons invariance classify three manifold? That is, if you use the generic gauge group G, for instance, G can be take any rank and any gauge group. We expect the Chern-Simons invariance can classify all three manifold. That's a kind of like a very, bold conjecture, but whether this T invariance can classify three manifold or not is totally, it's beyond my ability, totally. I'm not sure if I answered the question. Okay. Any other questions?
Can you comment on because in this example you mainly focus on this SU2, which just the two, yes. You have two and five brain. Can you comment on I mean, just want to I'm just curious how hard to find this connection, see if this abelian flat connections, if you want to generalize this 3D correspondence story from SU2 to SUN, maybe.
Good, very good question. So for plumbing graph, we know for general case, we know how to define general case, general GLN, whatever. So that's the definition given by Park, a surrogate student. But for this complement, it's still, we don't know, like when K is torus knot, we know how to construct f of K for higher rank gauge group. But for hyperbolic manifold, there is no, even singular example is not known. How to construct f of K for higher rank, for when K is hyperbolic knot. For torus knot, it's known by Park. So yeah, so higher rank is very difficult. Essentially, what we are looking at only this algebraic word for higher rank. But if you go outside of this plumbing or whatever, that's also same as in Jones polynomial. If you try to go to the higher rank, Jones polynomial, it's very difficult to find. Of course, there's a generic definition, but we don't know how to compute or so on. So, for instance, in the hyperbolic knot, instead of x, so if you go to hierarchy, you have x1, x2, xn. If you use a gln, if you use SLN, you have n-1. We don't know how to construct in general for this f of k for hierarchy. Also, very important conjecture, the important thing is the relation between z hat, large n limit of z hat, n goes to infinity. And then from the 5M brain picture, we expect that it's related to so-called topological partition function of the so-called toric-Calabi-Yau manifold. If you take, for instance, starting from, did I write the length space? Yeah, length space here. Starting from length space and take large n limit, that should be related to so-called Gopakma buffer invariance, okay, GB invariance of this toric-Calabi-Yau, like this type. The relation between this Z hat and this Gopakma buffer invariance is the open problem. It's a very good open problem. I think it's yeah, it's important. Yeah, it's worth investigating.
I see. That's very interesting. So,
Yeah.
So the toric, you may for the GV invariant of the toric manifold. So, do we know how to construct that toric manifold from the 3 manifold?
Yeah, this length space, of course, is an obvious candidate, but oh, I mean, it's already known that, for instance, if you RP3 is if you take large n limit, it should be this local P1 cross P1, L31 should be there's a 2-4 cycle. I mean, just but of course, I mean, the question is that somehow one has to somehow take nice regularization of this GB invariance or generating function GB invariance to compare Z hat. I tried once the comparison, but I failed. I didn't spend so much time because of the due to time limit, but it's a very, very interesting problem. Somehow you have to regularize topological partition function of this toric-Calabi-Yau to relate the Z hat invariance of length space.
Okay.
That's yeah. And of course, this as I mentioned, it's labeled by B, right? Flag connection depends on this flag connection is related to this Kera parameter here, Q1 and Q2. It's related to flag connection B. So essentially, roughly speaking, Q is equal to Qi is equal to Q to the Ni, and I is the taking value of this B. And Ni goes to infinity. That's a rough story. But the explicit relation is the open problem.
Okay.
So I also have a related question. So
yes.
Do you know the geometric relation between these 3 manifold and toric-Calabi-Yau threefold? Is it, for instance, is a 3 manifold some kind of special Lagrangian of that toric-Calabi-Yau?
Yes.
Okay, yeah.
No. Sorry. I'm sorry. I think so. 3 manifold. Let's see. So usual geometric engineering story is that if you take this n goes to infinity, you will see the toric type Calabi-Yau manifold. If the M3 is the length space, we know what is the corresponding manifold. But for generic M3, I think it should correspond to non-toric Calabi-Yau 3-4. If you take large n limit.
Oh, okay. So that's a large n limit.
Yes, large n limit. Yeah.
So I also have a generic question. So
yes.
Do you think you can obtain some kind of classification for all the 3D n equals to 2 ICFTs using this kind of construction from, for instance, from the 62,0 on a 3 manifold, just in general?
Good question. The answer is, I don't know, but I hope so. Because M3, the space of M3 is very big, and if you wrap the M5 on here, I really wish it will give you all possible 3D angle 2 theory, but maybe there's an exhaustive way to cook up the 3D angle 2 theory, but I don't know, to be honest. Because we know that the sum of a 4D angle 2 theory cannot be constructed class S, right? Class S. Sum of a 4D angle 2 cannot be constructed class S, but so that maybe there is such an example in 3D case. So, but yeah, the question is how to construct it, but I don't know.
Okay, any further question? Okay, if there's no further question, let's thank speaker Satoshi Nawata for the brilliant talk.
I hope it's understandable.
And thank you very much.
Yeah. I hope it's understandable to people.
Yeah, I think it's